Okay, so let us start writing here. If you remember, in case of semiconductor, if you draw the band diagram, then it's like that. Here, this is known as EV, that is valence band, and this is known as conduction band, right? And in between, this is known as EI. So what is EI? Intrinsic energy band, intrinsic Fermi energy level, EFI, you can say, right? And in case of doped, so let us say there are two types of doping, right? If you talk about doping, then how many types of doping?
Set 2.
P type and N type, right? So in case of it, if you talk about the N type, then there is a conduction, then a Fermi band, Fermi energy level, which is just lies below the conduction band, which is known as EFN. However, in case of P type, what happens if we talk about the P type EV, EC, then the Fermi level lies, that is EFP, just above the valence band. So the value of EFP, or you can say EFN, depends on the type of the material. And also this is known as the energy gap, that is Eg is equal to AC minus EV. Okay, so if I ask you the band gap energy for silicon, then anyone remember what are the band gap energy for silicon?
13.6.
13.6. No. So for the band gap energy of silicon, this is equal to 1.1 electron volt for silicon at room temperature. For the two materials, at least you have to remember the data. This is for silicon. However, in case of germanium, it is 0.66 electron volt at room temperature. So room temperature, what is the temperature at for room temperature? Anyone remember? I have already told you. So room temperature, it means that, unfortunately, if I say, then you people have very low basics. 300 Kelvin. You do not remember anything. This is not good. You should study at your home. Okay, so now let us talk about today's lecture. That is, what is the date? 24, right? So if I talk about today's lecture, that is 24/01/22. So first of all, let us discuss about the energy band diagram of MOS structure. Energy band diagram of MOS structure. So here M stands for, yes, MOS. So if someone asks you MOS, so what is the meaning of M? What is the meaning of?
Metal.
Yes,
Metal oxide semiconductor.
Oxide semiconductor.
metal oxide.
Semiconductor.
Good. So this is the way I expect from you all. You should answer. So metal oxide semiconductor, right? So if you recall your structure, the structure is like that. First layer is metal, after that oxide layer, and then after that semiconductor layer, right? If you remember our structure of MOSFET, this is the structure, right? Metal, oxide, and semiconductor, right? So it means that we have, so okay, so where is the junction? The junction is between, so there are two interface, or you can say junctions here, between the metal and oxide and semiconductor, right? G1 and G2 represents the junction. So if we are interested in finding the band diagram of MOS structure, so let us say here, case 1. So case 1 means that we are not applying, let us say VGS is equal to 0 volt. So what does it mean? It means that no potential, right? No potential. So if we are not applying any potential, then under this condition, so the device will be in equilibrium. So as it is, therefore the device will be in equilibrium. So now from onwards, whenever you listen the term equilibrium about semiconductor, then you have to understand that there is no bias, there is no external bias for the device. So if we will not apply any bias to any device like MOS structure or BJT structure, then the semiconductor will be in, then the device will be in equilibrium, under equilibrium you can say. So in, or you can say under equilibrium. So now we have to draw the band diagram. So since we know the band diagram for semiconductor, that is conduction band and valence band, and also there is a Fermi level, right? So similarly, now we have three materials, right? See here. If you see this diagram, then we have three materials. Metal is also a material, right? Yes or no? So we have three materials: metal, oxide, and semiconductor. So we have to draw the band diagram accordingly, right? So there are two interfaces. So let us say for case 1 we are drawing the band diagram. So band diagram will be like, let's say this is the two interfaces. Let us say this one, 1 and 2. So it means that here this side there is metal and here oxide. So oxide layer has some thickness. Let us say this thickness is given by D, which is in nanometer. And here the right hand side there is a semiconductor. Yes. So how we can draw the valence? How we can draw the band diagram? So let us say here there is for metal. For metal we have to draw the band diagram. So for metal there is no valence band. So here we will draw simply. We have to draw the line here. Okay. Okay. So now this is okay. So this is the metal exactly. So this energy, okay, so this level is known as vacuum. So this is the Fermi level of the metal. So from the Fermi level to the Fermi level to the vacuum, there is one term which is known as phi m, that is work function. So I will let you know what is work function. So under equilibrium, what will happen at the, since this is the band, this is the Fermi level for metal. So under equilibrium and from the Fermi level to the vacuum level, the energy is phi m, which is known as work function. So under equilibrium, assume the work function for metal and semiconductor are same. So let us say phi m represents the work function for metal and phi s represents the work function for semiconductor. So where phi m is the work function of metal, which is in electron volt. However, phi s is the work function of semiconductor in electron volt. Okay, so now here see, so this is the vacuum level, right? So vacuum level. Okay, so under equilibrium, I mean to say that the Fermi level for metal and semiconductor lies on the same plane. Okay, so okay, sorry, wait. So I say that Fermi level for metal and semiconductor lies on the same plane. So it means that, so here let us draw same plane. So this is for the metal. So for metal, so this is our semiconductor. So for semiconductor, which type of semiconductor we are using for NMOS? Anyone remember? Which type of semiconductor we are using for NMOS as a substrate?
P-type substrate.
P-type. So P-type. So as I told you, for the P-type, the Fermi level lies just above the valence band, right? So just above the valence band means here it will lie as EV. Okay, and for EC, so the EC will be, let us say this is here. Okay, EC. So as I told you, the under equilibrium, the work function for metal and semiconductor will remain same. So here this is phi s. So you can see the phi m, phi m and phi s is almost equal, right? So this is the oxide, and here left hand side there is metal, and right hand side there is a p-type semiconductor. So let us say this is p-type semiconductor, right? So now, so you can see here there is no band bending. Like this is a straight line, right? This is a straight line. So if in the exam, if I ask you to draw the band diagram of PMOS structure under equilibrium, so can you draw in this way? Okay, now there is one term. Okay, so this energy from the Fermi level energy to the vacuum level is known as work function. However, for the semiconductor, one more term arises, which is known as electron affinity, which is the energy between the conduction band and vacuum level. So this is represented by S. So where this is known as electron affinity. So since you people are very new, so you don't know the meaning of work function, that is phi and electron affinity. So I am going to explain what do you mean by the work function. So work function, it is the minimum amount of energy needed or you can say required, or you can say here required to eject an electron from the surface of a metal. Now another term, that is what is electron affinity. Electron affinity. So electron affinity, this is the energy difference between, from the diagram you can say the energy difference between the conduction band that is EC to the vacuum energy level. Okay. So whenever you, what is the need of work function? So whenever you design the MOSFET structure or MIS diode means metal insulator diode, or you can say metal insulator photodetector or metal oxide photodetector, then you need to know the value of metal function. However, if you design any device, let us say transistor, let us say diode, let us say light emitting diode, or you can say LED, let us say laser, if you design those devices using only semiconductor material, then you need to know the energy band gap. This is known as energy band gap and electron affinity. So let us say design consideration. So designing of any semiconductor devices, using semiconductor material, then you need to do two parameters, that is electron affinity, and second is band gap energy. These are the two most important parameters. However, to design MIS structure, here the MIS stands for metal insulator semiconductor, or you can say, so example is Schottky diode. Metal insulator structure. So this, to design this, we need to define work function, that is phi. Okay, so we are interested in finding or drawing the energy band diagram. So under case we have already drawn. So for this case, that is Vg is equal to 0, what do you think the current will flow from the device?
No, sir.
No,
No,
right?
sir.
So we are interested in case 2, right? So case 2, so under case 2, again there are two cases. We can either connect negative potential to the gate or potential to the gate. So what do you think? What should we connect? If we will connect the negative potential to the gate, then what will happen under this condition? The current will flow?
No,
No.
sir.
So why the current will not flow under VGS, if the VGS will be less than 0 for the N-type MOSFET.
No inversion layer will be formed.
No inversion. So why there will be no inversion? Because of the negative potential at the gate, what will happen? There will be a negative charge carriers there. So it will attract the holes from the P substrate to the region between N plus, right? Region between source and drain, just below the interface. So what will happen in that case? There will be no formation of channels. So if there will be no formation of channels, then what will happen in that case? There will be no flow of electrons, right? So we don't need to draw the band diagram for those cases. Now the second case is that is when we will apply some potential, some positive potential to the gate. So if we will apply some potentials to the gate, which is just less than, let us say, VGS, okay, VGS is less than VTH. So in this case, what will happen?
Very small current will flow.
Very small current, or you can say there will be a depletion region, right? Just below the interface between source and drain, right? So how can you bias? So we can bias the structures in such a way that you can see here. Let us say this is MOS, metal oxide semiconductor. So we have to bias in such a way that right here the VGS is less than VTH, right? So we have to draw. So because of the potentials applied to the device, what will happen at the interface, or here you can say under no bias? What is happening under no bias? The Fermi level for both metal and semiconductor lies on the same plane, right? So here, because of the applied potential under case 2, the Fermi level for semiconductor will shift upward. Okay, will shift upward. So what will happen here? You can see. So let us draw, and there will also be a band bending occurs. So here you can see for the oxide layer, there is a flat, right? Here you can see flat. So now here there will be a band bending occurs because of the applied potential. So we can see here there is a band bending occurs. So this is oxide layer, right? And on the left hand side there will be metal as per the structure, and here there will be a p-type semiconductor. P-type semiconductor. So let us see for the metal, let us say the Fermi level is here, right? EF. Okay. For, as I told you, because of the potential, what will happen? The Fermi level for the p-type semiconductor will shift upward. So the Fermi level for metal and semiconductor will not lie at the same plane. So here this is EFP, and okay, wait, and the valence band moves right away from the junctions. Valence band will move just right away from the junction. So here there will be EC. Okay. So what will happen? See here. Okay. So this is the applied potential, that is VGS, which is less than VTH here. So you can see why it is the valence band and conduction band move, or you can say shift away from the junction. Because what is happening under the VGS is less than VTH, there will be a depletion region, right? Near the interface of oxide layer and p semiconductor. So because of the depletion layer, in depletion layers, which type of charge carriers occurs? Immobile ions occurs there, right? In case of depletion layer. So it means that though the material becomes intrinsic there, right? So what will happen? So because of those intrinsic material, there will be a bending of band occurs. So here you can see, right? Okay. So now this region, so from this point you can see the band starts bending towards whenever we go closer to the interface, that is metal oxide semiconductor interface. So this width is known as the depletion width. This is known as depletion width, which is represented by, let us say, WD. Okay, so what is happening whenever the VGS is less than VTH? I mean to say that whenever we are applying positive potential to the gate, then in that case, what will happen? Just because of the applied potential, the Fermi level for the semiconductor will shift upward direction, and because of the intrinsic region between the just below the interface, metal oxide semiconductor interface, the valence band and conduction band will shift right hand side, and there will be a bending of the band occurs. So the width up to this width, what is happening? The bending is occurs. So this width is known as depletion width. Any doubt here?
No, sir.
Okay, so now what will happen? Now, if you talk about the case 3, that is case 3 is when VGS is greater than VTH. So under this condition, what happens? There will be inversion region, right? There is inversion occurs within the semiconductor just below the metal oxide semiconductor interface between source and drain, right? So now here we have to draw metal oxide semiconductor. So here we are providing the bias in such a way that here V is greater than VTH, that is V means VGS. So what will happen? Again, there will be a bending, no doubt. So because of the bending, see here, okay, so this is metal oxide and here semiconductor. So this, okay, wait. So as I told you, the Fermi level for the semiconductor will shift upward. So this is, let us say, EFP, and here just below, oh, it is not that much far, it should be closer. Okay. So again, here there will be a band bending. And because when the VGS is greater than VTH, so this up to this point is EC, EV, and this is, okay. So here, so because of the higher potential at the gate, this region is known as inversion region, and this region is known as depletion region. So what is happening when For case 3, sir, case 1, when we are not applying any potential, then there is no banding of band occurs, and also the Fermi level for metal and semiconductor lies on the same plane, right? What will happen whenever you will apply the potential which is just below the VTH threshold voltage to the gate, then during that time there will be a depletion occurs. So because of the depletion, there will be a banding of band occurs for the p-type semiconductor near to the junction. However, for VGS greater than VTH, then during that time or during this case, what will happen? There will be a banding of band occurs, no doubt. Beyond that, what will happen? There will be also a region for the inversion layer. Okay. Wait a moment. One call is coming from professor. Hello. So now, so we have already drawn the band diagram for 3 cases. Now we will do some mathematical calculations to find out. Now, next, what we will do that, next topic, we will do some mathematical calculations. Mathematical calculations to derive the expressions for depletion region, that is the width of depletion region, and inversion layer thickness, and their dependency on the doping concentration of bulk semiconductor. Okay, so let us start with a band diagram once again, right? So what will happen in that case? Let us, for the case 3, because case 3 is useful, right? Case 1 and case 2 is not useful. So let us do some calculations for the case 3. So case 3, what is the band diagram? Okay, so let us draw the boundary. Only we will consider the boundary here. Interface, I mean to say that. So let us say this is the oxide. So forget about the metal. So we will just draw the, let us say this is, and here this is so this is EFP and this is EV, right? So let us say here this there will be EC. So this is semiconductor, right? P-type semiconductor. So okay, P-type semiconductor. So what will happen? Let us say in the center, if you remember, in the center there is one Fermi level lie which is known as intrinsic Fermi level. Just here we can consider it lies in the center, that is EFI. Okay. So as I told you, there will be a band bending occurs due to the depletion region and the high concentration of electrons in the inversion layer as compared to the holes. So what will happen? There will be a bending of band occurs, right? So this is the case. However, for if we talk about, okay, so for, okay, this is the case, right? So here there will be EC, this will be EF, and this will be EFI. Okay, so the difference between, if you see here, this difference, that is the Fermi level, the energy band gap between intrinsic Fermi level and p-type Fermi level. So this term is known as phi b, where what is phi b? Phi b is known as, so basically what we are doing, let us say this position is 0 and this is x. So 0 is at the interface, that is oxide semiconductor interface, here at position 0, and this depth represent in depth of semiconductor. Right. So see here, phi b, where phi b represents, if you see the structure here, sorry, here, phi b is known as bulk potential. So how can you mathematically define? So phi b is equal to, if you can see the diagram, EFI minus EFP. Any doubt here to understand this term phi b mathematically? Yes?
Yes, sir.
Okay, so now this is known as bulk potential. So this side is surface, right? Metal oxide surface, and here this is semiconductor. So for the semiconductor region, we are calculating bulk potential. What about the surface side? We will have to calculate the surface potential. Okay, so surface potential, how can you define the surface potential? You can see here, the surface potential will be defined as, because, okay, see here, and the intrinsic region lies here. So this region is known as the surface potential, that is phi of S. Okay, phi of S is equal to surface potential. So mathematically, phi of S is equal to EFI, that is intrinsic Fermi level at the surface, right? So at the surface, this is surface. At the surface minus EFI bulk. Okay, so how can you understand this term? See here. This side, if you see, this is known as EFI bulk, because this is the intrinsic Fermi level in the semiconductor region. So this is known as EFI bulk. However, if you see here exactly the same point at the surface, then, sorry, this one. So this point, you can see, because of the bending, this point occurs here. So this is known as EFI surface, because this boundary will act as a surface, that is metal oxide surface. So at this point, we are getting the value that is EFI. However, in the semiconductor region, we are getting EFI bulk. So the value will be given as EFI surface minus EFI bulk. Now, if we are interested in finding the potential with respect to x means what is happening exactly? So this is the point where the band bending occurs. This is the point where from here, let us say this is width D. So what is happening? This point, so it means that phi of x represent the potential with respect to x, and x is the depth of semiconductor layer. So if you remember the structure here, see if you see, this is the structure. So here, okay, let us talk about the inversion layer. What is inversion? Okay, inversion. So VGS is less than VTH, VGS is greater than VTH. Okay, so what will happen? Here there is inversion, right? So what will happen? When we are interested in finding the phi of x, where x is equal to 0 at this point, and whenever you vary the x, it means that we are going into the depth of the p-type semiconductor. So with respect to the depth of the p-type semiconductor, how the potential will vary, we are interested in calculating that one. Okay, did you get my point? Yes.
Yes, sir.
Okay, so
Excuse me, sir.
yes.
So we declared phi s as work function for semiconductor. So
No. Phi of S. Where I have defined the phi of S is for semiconductor. I said phi of S is for the surface potential.
okay, sir.
Okay, maybe you will be work function you are talking about, right? Work
Yes,
function.
sir.
Maybe you are. Oh,
Yes,
okay.
sir.
I got your point. I got your point. So work function, the symbol for the work function and symbol for the bulk potential remains same, but meaning is
Okay.
different.
Okay, sir.
Okay. So here you can see. Okay, where I was. Okay, phi of S. So now we are interested in finding the bulk potential with respect to depth of the p-type semiconductor. So we will start, okay, let us say, so the expression is given by phi of S 1 minus x by WD square. So where WD is equal to width of depletion region, and x is depth in p-type semiconductor. So, right? So what will happen if, let us say, if x is equal to 0, then in that case phi of x or phi of 0 is equal to what will happen if you will put the x is equal to 0 in above equation 1, then
Phi of S.
phi of s. So what does it mean? It means that at x is equal to 0, we will get the surface potential. So exactly, we are getting the surface potential here. Because at x is equal to 0, this is x is equal to 0. This is 0. And here in that direction, we are varying the x. So at the surface, that is metal oxide surface, we are getting the same potential, cell bulk potential, that is surface potential. So this is equal to EFI surface minus EFI of bulk semiconductor. Bulk semiconductor means p-type semiconductor here. Okay, what will happen if the x becomes equal to WD? Okay, let me. What will happen if that is a position is equal to the width of the depletion region? Then in that case, what will happen?
0.
0, right? So it is electron volt. So we can calculate the bulk potential up to, or you can say less than width of the depletion layer, right? Okay, so now we will derive how much width will be the, for how much width, for what will be thickness, what will be the width of the depletion region, what will be the width of intrinsic inversion layer based on this calculation. So we have time. So let us see here the relation between potentials and concentrations of electrons, holes in the semiconductor. Everything is
Sir?
all about the semiconductor, electrons and
Sir?
holes. Yes.
सर phi s की वैल्यू बल्क माइनस सरफेस होगी ना?
It is all about the magnitude. Don't need to worry. Now it is fine.
Yes, sir.
Okay. So now see here. So since we are considering p-type semiconductor, right, for NMOS, so we are considering p-type semiconductor, p-type bulk semiconductor. Okay. So in case of p-type semiconductor, we represent the doping concentration by. Okay, so in p-type semiconductor, what will be the majority charge carriers? Just let us talk about this. In case of p-type semiconductor, what will be the majority charge carriers? Holes, right? Yes.
Yes, sir.
Okay, P. So we also, and what was the doping concentration? We represent the doping concentration by Na, if you remember the semiconductor. Okay. So in case of p-type semiconductor, the majority charge carriers are holes. And if you are interested in calculating the minority charge carriers, that is N, that is electrons, then how can you calculate? Do you know the relation to calculate the minority charge carriers? So anyone remember the law of mass action or mass action law? Yes. So according to mass action law, if you remember, the product of electrons and holes is equal to the square of the intrinsic carrier concentration at the constant temperature, right? So this is all according to the mass action law. This is, you must know, you have studied about this term in semiconductor, but you people have forget. So according to this, let us say P is the majority charge carriers and N is the minority charge carriers. So if you are interested in finding N, then Ni square by P, right? So similarly here, if you are interested in finding the number of electrons, or you can say concentration of electrons in p-type semiconductor, then what will be the equations? Ni square by Ni square by, yes, Na, because Na is equal to P. Okay, so this is all about the mass action law. Okay, also in semiconductor you have studied, if you want to find the concentration of holes, that is majority charge carriers, then P is equal to Ni. Ni is intrinsic carrier concentration, exp, that is exponential term, minus EFP minus EFI divided by KT. So what is this term? What is this term? That is EFP minus EFI. If you see the relation here, EFP minus EFI, then what you will get from this relation? Yes.
Phi B.
Phi B. Good. Phi B means bulk potential, right? So here you can write the equations in the form of this is equal to Ni exp, that is minus phi b you will get, because phi b is equal to EFI minus EFP, and here it is given EFP minus EFI. So here the expressions will be phi b by kt. So here you can ask me, what is K? K is Boltzmann constant. You need to remember the value of Boltzmann constant, and T is temperature. T is temperature. So this is all about p-type bulk semiconductor. Now at the surface, at the surface means we are interested in finding the carrier concentration at the metal oxide semiconductor surface. So now see here at the surface. So at the surface, because of the inversion layer, what will be the concentration there? What will be the majority charge carriers? Because of the inversion layer, what will be the majority charge carriers there? Yes. If you have understood the term, then you can answer me. Because of the inversion, electrons, very good, absolutely right. So because of the electrons, the majority charge carriers will be electrons, right? So the concentration will be N. N is the whole. So this is the concentration of electrons at the surface, right? Concentration of electrons at the surface. Okay, so this will be equal to, we have to just relate with this term Ni exp minus EFP minus EFI by kt, or just we have to relate with this term. So what will happen here? Ni exp bulk potential minus, sorry, surface potential minus bulk potential divided by kt. Okay, so from here, I mean at the surface, if you are interested in finding the minority charge carriers, that is, what will be the minority charge carriers at the surface? Due to the inversion layer, what will happen? What will be the minority charge carriers? Yes, holes, right? So holes at the surface, this is equal to, according to the mass action law, Ni square by Ns. So here Ts is equal to minority charge carriers, that is holes at the surface, right? At the surface. Now, what is Ni? Ni is intrinsic carrier concentration. Carrier concentration, right? Okay, so what is the unit of carrier concentration? I mean Ni, Pi, with Ni or N or P, what is the unit? In per centimeter cube, always remember. Okay, so in case of bulk semiconductor, p-type bulk semiconductor, what will be the majority charge carriers here? Holes, and minority charge carriers will be electrons. However, due to the inversion layer at the surface, the majority charge carriers will be electrons, and minority charge carriers will be holes. So do you remember these terms? Please remember. Now, here at the surface, phi s, what will be the phi s of value? That is phi s here with the doping concentration. Now we are interested in finding the relation between the doping concentration of bulk semiconductor and surface potential. So the relation is given by Na E square WD square divided by 2 epsilon 0 and epsilon r. So here, let us say this is equation 2. So here Na is doping concentration of p-type doping concentration. Okay. Okay, doping concentration of p. Okay, no problem. Doping concentration of p-type bulk semiconductor. And E, that is the charge of electron. And what about the WD? This is the width of depletion region. Okay. Now, what about the epsilon r? This is the relative permittivity of semiconductor material. And what about the epsilon 0? What is epsilon 0? Yes?
Permittivity in free space.
Free space. Good. So now, what will happen under? Okay, wait 1 minute. Wait a moment, because we have limited page here, so we will have to lecture 4, right? Okay, so now we will continue here. So what will happen now? We will drive. We are in the final stage. Just we need 5 to 10 minutes. After that, we will leave the class. Okay. So now under a strong inversion. So what will happen if we will keep on increasing the gate to source voltage? So under a strong inversion, means what will happen in that case? Yes, the number of electrons will keep on increasing just below the surface, right? Just below the interface, right? So what will happen under the strong inversion? We have the condition that is the material in the depletion region will become intrinsic. That is, it means that Na is equal to Na, that is the number of electrons at the inversion layer will almost equal to the number of the doping concentration of the p-type semiconductor. So here in the inversion layer, the number of concentration of electrons will almost equal to the doping concentration of p-type semiconductor. So in that case, the surface potential, that is phi s, will be equal to twice of the bulk potential. So which is given by 2 kT ln Na by Ni. So we know very well what is K and what is T, what is Na, what is Ni. So we are not going to define here. So now let here under the strong inversion, Wm represents the depletion width, or you can say region, in a strong inversion. A strong inversion. Okay, so now I will continue from here. Wait a moment. Okay, so now what will happen when we have assumed the omega m is equal to depletion region in a strong inversion. So here we know from the above equation that is phi of s is equal to 2 phi b, which is equal to 2kt ln Na by Ni, and we also know that, okay, so from these equations, therefore 2kt ln Na by Ni, and we also know that the phi s is equal to, if you remember, phi s, okay, here I am showing, oh, where is it? Okay, so phi of s is equal, sorry, phi of s is equal to Na E square Wm square by 2 epsilon 0 epsilon r. Since we know very well phi of s is equal to Na E square W d square by 2 epsilon 0 epsilon r, right? We know very well. So since under a strong inversion, we are assuming the width of the diffusion layer is Wm. That's why we have replaced Wd by Wm here. So from these equations, what will happen? From these equations, what will happen? Okay, let us rewrite the equations. Okay, here it is the term. Okay, so okay, now we can write cross multiplication here so that we can get the expression for Wm. So here 2 into 2 4 epsilon 0 epsilon r kt ln Na by Ni, which is equal to Na E square Wm square, right? So what will happen through these equations? So we can write Wm square, which is equal to 4 epsilon 0 epsilon r kt ln Na by Ni divided by Ni E square, right? So if you want to write Wm, which is equal to a square root under 4 epsilon 0 epsilon r kt ln Na by Ni divided by Na E square. So we can also rewrite these terms in this way: Wm, that is width of depletion layer under the strong inversion, which is equal to 2 multiplied by epsilon 0 epsilon r kt by Na E square ln Na by Ni. So this is the expression for depletion width under a strong inversion. Okay, so under a strong inversion. Now next, what will happen? Next, so under a strong inversion, we know very well phi of s is equal to 2 phi of b, right? So what will be the position, what will be the bulk potential with respect to x? If you remember, phi of x is equal to phi of x is equal to phi of s 1 minus x by wd square, wd the whole square, if you remember, right? So under a strong inversion, under strong inversion, the phi of S is equal to phi b. So it means that phi b is equal to phi of S by 2, right? Okay. So under strong inversion, what will happen? We know very well at x is equal to Wm, we know very well phi of S becomes equal to at x is equal to Wm, phi of S is equal to phi of x, yes, phi of x. Okay, let us forget about it if you do not remember. So under the strong equilibrium, under the strong inversion, this is the conditions we know very well. So we are interested in finding the phi of x is equal to phi b under the strong equilibrium. So according to this relation, what will happen? Phi of b is equal to 2 phi b, because phi of x is equal to phi of s. So phi of x is equal to phi b under a strong inversion, and phi of s will be replaced by 2 phi of b. So 2 phi b bulk potential. Okay, so this will be equal to 1 minus x by, here we will write Wm, because under strong inversion the width of the depletion region is Wm. So now here phi b will be cancelled, so 1 is equal to 2 root under 1 minus x by Wm square. So if you will rearrange the term, then you will get, see, 1 by root 2 is equal to 1 minus x by Wm. So it means that you will get here the term that is x by Wm, which is equal to 1 minus 1 by root 2. So it means that if you are interested in finding the x from here, then x is equal to 2 minus under root 2 multiplied by Wm. So this is the expression for equation 4 is known as the width of inversion layer, or you can say region. So any doubt here? Yes?